This video is going to focus on specific heat, and more specifically, we're going to look at calorimetry and the idea of heat transfer and do problems involving that. So let's talk about heat capacity first. Heat capacity, or CP, is the amount of heat needed to increase the temperature of an object by 1 degree Celsius. So if you wanted to raise the temperature up of an object by 1 degree Celsius, how much heat would you need? This is obviously an extensive property because it's going to depend on the amount present. Obviously, if you wanted to raise the temperature of an ice cube by 1 degree Celsius, it's not going to take that much energy. But if you want to raise an entire iceberg, which is the same substance as an ice cube, it's still water. If you want to raise an iceberg by 1 degree Celsius, obviously it's going to take a lot more energy here. All right, so this is an extensive property. The amount matters. So you really couldn't compare substances here, if you will. So we kind of came up with something here called specific heat capacity, or C or CP here. Basically, this is the amount of heat you need to raise 1 gram of a substance by 1 degree Celsius. Now you can kind of compare substances here because they all are dealing with the same amount. We call that specific heat capacity. Water has a relatively high specific heat, 4.184 joules per gram degree Celsius, and you should be aware of that. You need to know that number. All right, the specific heat of water is 4.184 joules per gram degree Celsius. And I know you might think like, oh, well, that number doesn't seem that high, but keep in mind here, metals basically have a specific heat kind of with decimal numbers. So it is a pretty high specific heat. What that means is if something has a high specific heat, that means you need a lot more heat, a lot more energy here to raise the temperature up. Metals, on the other hand, have a relatively low specific heat, and you need less energy to raise the temperature. The easiest example I can give you is if you took the equal amounts here of water and a metal and put them in a parking lot on a hot summer day, the sun shining on them, right? If you went out a few hours later and you had to touch one of them, you would obviously want to touch the water because it's not going to be as hot as the metal because it has a high specific heat. It takes a lot more energy to raise the temperature. And this is, very important because otherwise on a hot summer day here, if the water had a low specific heat, the temperature of the oceans and lakes would immediately rise up, all right? And then the organisms in the water would obviously not be too happy here. So even if you think about it in terms of, having a string of hot days in the summer, your pool isn't immediately going to be, 100 degrees. It takes a lot of days here of 100-degree weather to even raise the temperature up. And this is because water has a relatively high specific heat. So obviously you should understand this idea of specific heat and realize water is a relatively high specific heat here, and definitely know that it's 4.184 joules per gram degrees Celsius. So another example here of this idea of specific heat, if you put a wooden spoon and a metal spoon in a pot that's cooking on the stove, and you went up to the spoons, the metal spoon would be too hot to touch after a while because it has a very low specific heat, whereas the wooden spoon has a higher specific heat, so you could go up and grab it and you don't feel the heat in that spoon. And this is also why you use metal for your pots and your pans because they have a lower specific heat, they heat up faster, and they cook your food better with less energy. Here's just another example to make sure you understand this idea of specific heat and the fact that water has a high specific heat. So if you took equal amounts of gold and water here and started heating them, all right, you will see here gold would get to a much higher temperature in the same amount of time compared to the same amount of water. Gold here you can see is at least at 90 degrees Celsius, and water is somewhere around 20 degrees Celsius, heating them for the same amount of intensity, same amount of time, same amount of gold and water here. And this is because water has a relatively high specific heat. It takes a lot more energy to get the temperature of the water to go up here. All right, it can basically hold a lot more of that energy, if you will. All right, so definitely understand this idea of water having a higher specific heat. Now we're ready to do some specific heat problems here. We already said the units for specific heat are typically going to be joules per gram degree Celsius. It's some form of energy unit per mass unit times a temperature unit. So maybe you could see this in like calories per gram degree Celsius, all right? But get used to seeing that joules per gram degree Celsius, that's the units for specific heat. So the equation we use for this is Q equals mc delta T, all right? Sometimes kids like to call this Q equals mcat, all right? So you need to know the equation, that's first, but you also need to know what each of the letters means and what the units should be for each. That's very important here, all right? You can't do these problems if you don't know the equation and you don't know what the letters mean and what the units should be. So Q is going to stand for the heat or the energy here, and it's going to be in joules. Q is not temperature, it's heat. It's typically going to be in joules or something like calories, all right? M is mass, and that's going to typically be in grams. C, we already said, is specific heat. It's going to be typically joules per gram degree Celsius. The units of your specific heat are basically what's driving the other units in the equation. And delta T stands for the change in temperature. It's not just T, it's not just the temperature, it's the change in temperature. So it's always the final minus the initial temperature, and it's typically going to be in degrees Celsius. So you got to watch these units here. Make sure your units are right when you're setting up these problems, but you need to know what each of the letters mean. So Q equals mc delta T. You definitely need to know this equation and be able to use it in problems. Let's jump right in and try one of these problems. So for this example, it says when 435 joules of heat is added to 3.4 grams of olive oil at 21 degrees Celsius, the temperature increases to 85 degrees Celsius. What is the specific heat of the olive oil? All right, so we immediately know we have to use our Q equals mc delta T equation. All right. And you have to figure out what letter am I solving for. Typically for these problems, you're going to be solving for one of the letters, and that means you know everything else in the problem here. So the question is asking us to find the specific heat of the olive oil. So remember, specific heat is C. So you need to know what these letters mean so you can figure out your problems here. All right, that must mean you know everything else in this problem if you're solving for C. So let's start plugging in. Q. All right, in your head, you should be saying, okay, what is Q? Oh, Q is heat. Typically, it's going to be in joules. Well, they gave you 435 joules. So you know the value of Q, right? M is going to be the mass. They told you had 3.4 grams here. C is what we're solving for, so we're going to leave that as our variable. And delta T is the final minus initial temp. So you got to be careful here. You're typically going to have two temperatures. You might have to sift through the problem. The higher number does not automatically make it the final temperature, so be careful. But this problem does say the temperature increases to 85. So that's what we're increasing to and ending with. So 85 is our final minus our initial. They told us it was at 21 degrees Celsius. So delta T is final minus initial. All right, so we plugged everything in. Now we're just ready to do math here to solve for C. All right, so I'll show you how to do this, and then I expect that you'll be able to do this math every time. So the first thing I would do to solve for this one is I would do my subtracting here, the 85 minus 21, and I'd get 64 degrees Celsius, okay? So now what you're going to do here is I would multiply the 64 times the 3.4. So you can drop off your units here as long as you pay attention to your final answer, having the units, what units it should be, all right? Make sure you're plugging in the correct units here for the problem. Mass is typically grams, specific heat is typically joules, temperature is typically degrees Celsius, and so on. So when you take the 64 times the 3.4, I have the 435 equal to now the 217.6 times C. So all I did was subtract the 85 minus 21 first, got 64, 64 times 3.4, and now I have 217.6 times C remaining on the right, equal to the 435 on the left. So I have to solve for C. So you divide both sides now by the 217.6, and then you will now be able to solve for C here. So you do need to watch sig figs, all right, Typically here, we're doing a lot of multiplying, dividing, so go back to your original problem, count sig figs and use the least. So it looks like in this problem, the lowest amount of sig figs we have are 2. So your answer has to have 2 sig figs. So when you round this correctly and you do the math, it should come out to be 2.0 with 2 sig figs. I think it comes out to be like 1.99 something. So 2 sig figs is 2.0. And be careful with your units. You were solving for C, which is specific heat, and you need to know that specific heat has joules per gram degrees Celsius. All right, and those units do check out here in this problem. All right, this is not something you can just guess on. You have to know this. The units for C are joules per gram degrees Celsius. So that has correct sig figs. It has units. I, circled my final answer and I showed all my work. This is the minimum amount of work you would need to show here to get full credit on one of these problems. So know what the letters mean, know what the units should be, then you just plug in and solve and watch your units and sig figs. So let's try another example here. This problem says how many calories does 32 grams of water absorb when it's heated from 25 degrees Celsius to 80 degrees Celsius. So I know it's going to be a Q equals MC delta T problem. They're asking how many calories. So in your head, you're going to say, okay, which of these letters would give me calories? Well, calories is a form of heat, so it's going to be Q. Remember, typically here in these problems, this is where knowing your units is important. Q is going to spit out joules. Well, they want calories. So that means you're probably going to have to make a note to yourself and say, oh, I'm probably going to have to convert at the end of this problem. So be careful. You do got to watch your units here with these problems. All right. Q is going to typically spit out joules, not calories. That's something you'll have to watch for. So that means I'm solving for Q. So that means I should know everything else in the problem. I'm just going to start plugging in and solving. So for the mass they gave me was 32 grams. Do I like grams for mass units? Yes, that's what I want. So I don't have to worry about converting that. All right. C here, specific heat. In your head, you should be saying, okay, well, typically that's joules per gram degree Celsius. You might say, well, oh, I don't see a specific heat in this problem. I know that I'm solving for Q, but I don't see the specific heat here. Anytime you have a problem like that, where you're like, I know I'm solving for like a different letter, but I don't see, specific heat anywhere in the problem, pay attention to the substance. We're using water in this problem. Anytime you have water, you are supposed to realize that you know the specific heat of water. All right. Remember, the specific heat of water is 4.184 joules per gram degrees Celsius. So just watch for that. If you're using water, you are supposed to remember that you need to know the specific heat of water. 4.184 joules per gram degrees Celsius. And then delta T is the final temp minus the initial. So it looks like we're going from 25, which was our initial, to 80, which was our final. So 80 minus 25 degrees Celsius here. So this one, the math is a little bit easier to solve. Again, I would do my subtracting first, and you get your 55 degrees Celsius. And then I would just take 55 times 4.184 times 32. When you do that, you should get 7363.84. And remember, your units for Q, this is where you need to know your units. Your units for Q here should be joules. All right, if you pay attention to your units up there in the problem, the grams would cancel out, the degrees Celsius would cancel out, you'd be left with joules. So yes, the problem wants calories, but your Q is in joules. So you're going to have to convert here. So multiplication symbol, conversion line. I know that joules need to go on the bottom for them to cancel. The conversion here is that there's 4.184 joules for every 1 calorie. Joules on top and bottom, they cancel. Now you're in calories. You do need to watch your sig figs. So go back to your problem, count sig figs, use the least. It's going to be 3. So your answer for this should be 1760 calories. All right, that's correct. Units and sig figs. All right, so this is just showing you another different example here for Q equals MC delta T, specific heat problems. And remember, you do need to know the specific heat of water. Now we want to look at this idea of calorimetry. This is just the idea that we are measuring heat here by looking at temperature changes when something either takes in heat or gives off heat. So calorimetry is just talking about we're measuring heat by looking at temperature changes. A calorimeter is a device that we use to measure heat. And it's got to be something that's a good insulator here. So typically we use foam cups. All right. I know that might sound a little bit weird, but foam cups are pretty good insulators. So we will do calorimetry experiments with kind of a cup inside of a cup. So you can kind of see the basic setup here in the picture. You kind of have an outer cup, and then you have an inner cup where your experiment or your reaction is taking place. All right, so you have some type of reaction mixture in that inner cup, and then you usually put a thermometer in, maybe a stir, and you cover it up in some way. And the idea here is that we're not going to lose any heat to the surroundings because of these foam cups being good insulators. And all you're doing is mixing two things basically and measuring the temperature of the reaction. That's calorimetry. It's literally just measuring the temperature here, the temperature change of a reaction, a beginning temperature and an ending temperature. So a lot of times we might call this coffee cup calorimetry. Uh, Q is going to be equal to the change in enthalpy here. So at these conditions, we're basically assuming no heat is being lost to the surroundings because of these cups being good insulators. So anytime you hear calorimetry, just realize we are looking at heat. We're going to be measuring the beginning and ending temperatures here. I just want you to see a more advanced calorimeter here. This is called a bomb calorimeter. Obviously, we don't have one of these. We're going to be using the foam cups, but this is just a sealed vessel here. It can withstand very high pressures here, and your reaction will be taking place inside of it. All right, so it's just another form of calorimetry where you are going to be measuring the beginning and ending temperatures, but they do get more advanced, obviously, than just using foam cups. And that's what I wanted you to see with this. This is the basic setup of our calorimeters that we'll be using. We just take a foam cup and we put it inside another foam cup, and this works well for our reactions. Basically, we can assume that no heat is lost to the surroundings here. And again, you will have your reaction taking place in the inner cup. Usually we will be measuring with a thermometer, maybe a stirrer in there to stir it up, and it's going to be covered here in some way. And we're just going to measure the beginning and ending temperatures and then do some calculations with this. A very important idea that we will be using here in these calorimetry problems is this idea of plus Q equals minus Q. The basic gist is that the heat that is gained by your system, all right, must be equal to the heat lost by the surroundings and vice versa. So what does this all mean? Basically, any heat that's lost by a particular substance would be equal to the heat gained by your water. So for example, if you took a hot metal and put it in water, obviously the temperature of the metal is going to drop, it's going to cool off, and the temperature of the water is going to increase. Well, according to the law of conservation of energy, you can't just create or destroy energy, right? The water can't just magically gain temperature. It had to come from somewhere. It was the energy that was lost by the metal. So the amount of energy that the metal lost here, negative, is equal to the amount of energy that the water gained. Plus Q equals minus Q. However much the metal lost, that's equal to the exact same amount that the water gained, because you can't create or destroy energy here. All right, so that's a very important idea that we need to be able to use here. Plus Q equals minus Q. So we can actually do reactions now taking place in the water, and we can use this idea. All right, the amount of heat that's gained by the water, all right, we can measure that with our temperature change, is going to be equal to the amount of heat that was lost by the reaction. All right, so this idea is going to be very important in problems. And when you're using this, you should get used to writing this plus Q equals minus Q here. All right, so we're going to use this very simple setup of a calorimeter to measure these temperature changes. And because this is taking place inside a calorimeter, we're assuming that no heat is being lost to the surroundings. So any heat that's lost by your reaction is going to be gained by your water. And if you can measure that heat, you could quickly figure out how much heat was lost by the reaction and vice versa. All right, so this is a big idea we need to use here. So now we're going to try another problem here. All right, if you notice, there's a lot more going on here, but I'm going to point out how you know this problem is different. So first, we have an unknown metal with a mass of 75.8 grams heated to a temperature of 80 degrees Celsius. It's placed in 79.4 grams of water that is at a temperature of 18.5 degrees Celsius. The temperature of the water and the metal then rise to 23.5 degrees Celsius, and we want to know the specific heat of the metal. All right, so the key is, how do you know if a problem is a simple Q equals MC delta T, where you just plug in and solve for one of the unknowns, or if it's one of these plus Q minus Q problems? So you have to be able to look at a problem and know, hey, look, it's just a simple Q equals MC delta T, or it's going to be a little bit more fun, plus Q equals minus Q1. The key here is, if you're just talking about one substance, it's going to be a Q equals MC delta T problem. If you notice all the other examples we did, the one was using just olive oil. It was talking about just olive oil. That was a Q equals MC delta T problem. The other example we did was just talking about water. One substance, Q equals MC delta T problem. All right, as soon as you start mixing substances or taking a substance and putting it in water, boom, you know that's a dead giveaway. It's going to be a plus Q equals minus Q problem. All right, so you do have to be able to pick that out in the problem. I can see in this problem that I have a metal being heated and placed in water. That's a dead giveaway that immediately I know is going to be a plus Q equals minus Q problem. These problems do take up space, so I'm going to try to fit this all in here. But you need to write that. The plus Q equals minus Q must be written, because that's going to allow you to do the sign switcheroo in the problem. All right, and I like to label this. I like to say, okay, in this problem, who's going to be the minus Q and who's going to be the positive Q? So in this problem, who is losing the heat? Well, think about it. If you're taking the hot metal, you're putting it in water, the metal's going to get cooler. So the metal is going to be losing the heat, and then the water is going to be gaining that heat. So any heat that is lost by the metal is going to be equal to the exact same amount of heat that is gained by the water here. That's why it's a plus Q. All right, so you must have the plus Q equals minus Q written, or you lose points. All right, so now it's important to say, okay, what are we solving for in this problem? So this problem says, what is the specific heat of the metal? All right, so that means in this problem, we are going to need to end on the metal side. All right, as long as we're not solving for the final temperature, you can kind of split this up into two separate problems, and it kind of makes your life a little bit easier. So I know that I'm trying to find the specific heat of the metal. So that means I want to end on the metal side. So that means you start on the other side. So I'm going to start on the water side here. All right, so you would say, okay, well, what's the Q of water? Well, remember here, you do know what Q equals. Q always equals MC delta T. So you're going to start with Q equals MC delta T, but we're specifically starting on the water side. So all these numbers are going to relate to the water only. That's very important. There's a lot of numbers in these problems. You got to watch your units, and you got to pay attention to what you're doing. You really need to think through these problems. So I'm going to end on the metal side. So that means I'm starting on the Q of the water side, and we already know that Q equals MC delta T. All right, so there should be just one thing that you don't know here in the problem for Q equals MC delta T for the water. So if I look at the problem, Q I know is joules. Do I see anything relating to joules here for the water? No. So that means I must be solving for that for the water. I don't know the Q of the water. So that must mean I know everything else about the water. So the mass of the water. If you look at the problem here, they told me the mass of the water is 79.4 grams. Right? We want it to be in grams, so that's good. C. C is specific heat. That's typically joules per gram degree Celsius. I don't see that anywhere in the problem. But remember, this is water. So you need to know that it's 4.184 joules per gram degree Celsius for water. You need to know the specific heat of water. And then delta T is final minus initial. So it says that the final temperature of the water and the metal is 23.5. All right, realize here, because the water and the metal are sitting together, you took the metal and put it in water, they always end up at the same final temperature. So they may not specifically say that the final temperature is for the water, but realize if you know the final temperature of the metal, you know the final temperature of the water. All right, minus the initial. Remember, delta T is final minus initial, and the initial temp of the water was 18.5. All right, so when you do your math here, do your subtracting first, multiply it by 4.184 times the 79.4. The Q of the water comes out to be, remember, don't sig fig this yet, don't round this yet. It comes out to be here 1661.048, and your units for Q are joules. All right, so what this is saying is that when you take this hot metal and put it in water, the water is gaining 1661.048 joules, right? But where did that come from? Water can't just magically gain energy. The law of conservation of energy says that can't happen. So because we wrote this plus Q equals minus Q, if the water gained that much energy, that much heat, it had to come from the metal losing it. So now you know the Q of the metal is equal to the negative of that number. Okay, because you wrote the plus Q equals minus Q, you can do the sign switch here. All right, all you did was take that exact value and put a negative in front of it. So the amount of heat that is lost by the metal is equal to the amount of heat that was gained by the water. The only difference is the sign here. So now we know something about the metal side. So now we're ready to move up. All right, we're ready to take our problem and go up here and deal with the Q of the metal side. We said that's where we wanted to end. So you might say, okay, well, I don't know anything about the Q of the metal other than this value down here. Well, that's not true. You know Q for the metal is going to be equal to MC delta T, all right? So it's just a second Q equals MC delta T problem here. So plug in what you know and solve for your unknown. So for the Q of the metal, we just said, we found this here at the bottom. That's going to be negative 1661.048 joules. The mass of the metal, according to the problem. Now you got to be careful here. This is where your organization is important. You have to make sure you're realizing you're dealing with the metal side now. So you need to pick out the numbers relating to the metal. Well, it told me that there was 75.8 grams. Grams are the units I want. C for the metal, that's what I'm solving for. I'm solving for the specific heat of the metal. And then delta T of the metal, final minus initial. Remember, the metal and the water are at the same final temperature. So 23.5 is the final temperature of the metal minus the initial temperature of the metal. Be careful here. Make sure you're picking out the right temperature. And that was 80. Okay, so if you notice here, it's very important to point out, when you do your subtracting for your final minus initial for the metal, it comes out to be negative. Does that make sense? Well, yes, because the metal got colder. So it essentially lost temperature. Not to mention, the negative from your temperature change would cancel with the negative for your Q here, and that would give you a positive specific heat. It would cancel out. You can't have a negative specific heat. So now you just got to do your math and solve for C. All right, so we saw an example like this where you had to do the math to solve. So when you do solve for C with correct sig figs and units, it should come out to be 0.388 joules per gram degrees Celsius. So make sure you can actually plug that in and get that number. All right, and because it's specific heat, it's joules per gram degrees Celsius. So the easiest way to do these plus Q minus Q problems are to figure out which side you want to end with, start on the other side, and then do your sign change, and then finish the problem on the side that you need to end with here. So essentially, it's two Q equals MC delta T problems. Remember, you need to look at the problem and realize it's a plus Q minus Q problem because you are mixing two things, or you're talking about taking one substance and putting it in another. That's how you know it's one of these plus Q equals minus Q problems. If all you're doing is talking about one substance in your problem, then it's just a simple Q equals MC delta T. So you can set this up as two kind of separate problems as long as you're not solving for the final temperature. All right, because the final temperature is the same on both sides, if you were solving for the final temperature, you would have to set this up as one massive equation and solve for your variable. Because you wouldn't know it on both sides, you would have too many variables. You would have to set this up as one massive equation. But as long as you're not solving for the final temperature, you kind of solve one side and then you go and get the answer you're looking for on the other side. So plus Q equals minus Q. Definitely a big idea you need to be able to do these problems. We can actually take this idea of calorimetry and take it a step further here, and we'll use it to actually find the enthalpy of a reaction. So there's some steps involved here, and sometimes, you might not need to do all of these steps. So I'm giving you basically kind of a nice overview here of some of these problems, and then we'll have to look at some other examples. So you can use the density to determine the total mass of a solution. So if you're mixing things here and you need to know the mass of your solution to do your Q equals MC delta T problem, you can use density to help get to that mass if the mass isn't given. So just keep that in mind. Density can be useful in these problems to get mass. We're going to assume the specific heat is 4.184 joules per gram degrees Celsius. Unless you're told something else, sometimes you might even be told that it is 4.184 joules per gram degrees Celsius. If we're dealing with water here, we're assuming that's going to be the specific heat. And we will solve for Q. So essentially, we're doing a Q equals MC delta T problem. We might have to use density to get to mass. We might have to use 4.184 here as our specific heat, but we'll get to Q. But the key here is we were measuring the temperature of the water. Well, that's the temperature change of the water. So you have to realize here that we're actually wanting to look at the reaction that took place in the water. So we're going to have to flip the sign here. Right? And that's something we have to remember to do in the problem. We're going to be measuring the temperature of the water, but we care about the reaction that took place in the water. You might have to determine the moles of the substance formed here, depending on what's asked. And you might even have to do a limiting problem if it's asking about one of the products. But the key is if you take that Q, right, get it to kilojoules, and then divide it by your moles, that'll give you your delta H of the reaction. Think about it, you'd be in kilojoules per mole of the reaction here. So we can take this idea of Q equals MC delta T, find Q, and then get it to kilojoules per mole to be able to have our enthalpy change of a reaction. But there's some different variations of these problems, so obviously we need to look at some examples. For this example, it says in a calorimeter, 100 milliliters of 1 molar NaOH and 100 milliliters of 1 molar HCl are mixed. Both solutions were originally at 24.6 degrees Celsius. After the reaction, we have a new final temperature here. We're going to assume all the solutions have a density of 1 gram per centimeter cubed and a specific heat of 4.184 joules per gram degree Celsius. And we want to calculate the enthalpy change here in kilojoules for the reaction. So they're only asking us for kilojoules here. They're not asking us for kilojoules per mole. So that's something to kind of be aware of. But you need to realize you're mixing two solutions and you're measuring a beginning and ending temperature. So this is going to be a Q equals MC delta T problem. All right, so we're going to need to plug in a mass, a specific heat, and our change in temperature. Before we can do that, you need to realize they gave us milliliter amounts of both substances that we are mixing. So we're going to mix these things, and then we're going to have a mass of our overall mixture here of our new solution. And this is where the density will come in. All right. Understand that when you mix 100 milliliters and 100 milliliters, now you have 200 total milliliters. So we're going to have to use this idea that there's 1 milliliter for every 1 centimeter cubed. And then based on the density they gave us, we know there's 1 gram here for every centimeter cubed. So this was a pretty easy conversion here involving the density because the density was just 1. But I want you to see how we use our total milliliters to get to our mass by using the density. So obviously here we're going to have 200 grams as a mass of our mixture when we mix these two and the reaction is going to take place. So now we can plug in here. Q is going to be equal to the mass, which we said is 200 grams. Watch your unit on the mass. Obviously, it needs to match the mass units involved with your specific heat. So now we're at C, which is the specific heat. The problem tells us to use 4.184 joules per gram degrees Celsius here. If they don't tell you anything about this, obviously this would be the number you're using. We're assuming that the specific heat of this solution, because both of these are in water, would just be the specific heat of water. And then we have to do our delta T, final minus initial here. So the final was 31.3 minus the initial 24.6 degrees Celsius. So now you just need to solve for Q, all right? So when we do the math here, do your subtracting first and then multiply everything through. We get 50, we get 56 06.56 joules. All right. But realize here, this is something you need to understand. This is the Q of your solution. Essentially, this is the heat of your mixture. So the solution, because this is positive, gained that many joules of heat here. Realize your units for Q are going to be joules. So the solution gained that much heat. But where did it come from? Well, that's where you have to use this idea of plus Q equals minus Q. So if the solution gained that much, that means the reaction that took place here lost that value or negative that value. All right, so that's a very important idea that you need to understand. Essentially, we are using here this idea of plus Q equals minus Q. Essentially, the heat gained by your solution is equal to the heat lost by your reaction. If you're measuring the water to have gained 5606.56 joules, it had to come from somewhere. It came from the reaction taking place, and that's what we care about here. So that's the heat that was lost by our reaction, right? But that doesn't fully answer the question here yet. They did not ask us for this in kilojoules per mole. They're just literally looking for the enthalpy change or the energy change involved here. So I just have to take this a little bit further. If my Q is negative 5606.56 joules, well, we just want this now in kilojoules. All right, so that's an easy conversion. There's 1,000 joules for every kilojoule. Your joules cancel. And when you plug and chug here and watch your sig figs, your overall energy change here is negative 5.6 kilojoules. All right, so we didn't need kilojoules per mole here based on what the problem was asking us, but make sure you understand this idea of how we mixed these two solutions, got their mass using density, plugged into our Q, and then once you realize here that that's the Q of the solution, you have to do this sign flip because of plus Q minus Q, now you have your energy change here for the actual reaction that took place. And just watch your units with these problems. So this is just showing you kind of a different version of a calorimetry problem, all right? And there's even more here that we have to kind of consider. We're going to look at another example here. This one says an experiment was conducted in which 5.19 grams of sodium carbonate was dissolved in 75 grams of distilled water. A temperature increase of the system of 3.80 degrees Celsius was observed. We want to find the molar enthalpy of dissolution of sodium carbonate. So there's something here we really need to watch, and it's something you have to be careful of. If you're given one of these problems where you're adding a solid here and it's just dissolving, so there's a lot of words they could use here. They could say that the solid was dissolved in the water. They could say heat of solution or heat of dissolution. All right, that's telling you the solid was just dissolved. That's all that took place. The solid dissolved, and there's some energy change that took place when this solid dissolved. So it's not a reaction, it's literally just a dissolving, a phase change essentially. If you're given a problem like that, where it's just dissolving, all right, or dissolution here, you add the water and the solid mass together for your total mass in your specific heat equation. So you're going to need a mass in your Q equals mc delta T. Well, if all that's happening is you're dissolving and it's not a reaction taking place, your mass is going to be the solid plus the water. Because here, essentially, when it dissolves, that solid is now incorporated into the water and you have a new solution. So you need to use the total mass here in your specific heat equation. So you need to be very careful of this, all right? Obviously, in this problem, it says that the sodium carbonate is dissolved in a certain amount of water. So boom, immediately you should be saying, okay, I need to add the mass of the solid to the mass of the water for my specific heat equation because all that's happening is it is dissolving. Again, dissolution means the exact same thing. You would add them together here. This is going to be a little different if all that's happening is it's just reacting, as you will see on the next kind of part here. If you're doing one of these problems and the solid is being burned, combusted, or reacted in the water, then you're just going to use the mass of the water only. You're not going to add them together when you do your mass here for your Q equals MC delta T. There's a huge difference here. Essentially what's happening is, in this case, there's a reaction taking place in the water, and any of the heat transfer to the water, all right, is happening because the reaction is taking place in the water. The substances or substance is not being incorporated into the water. The water is just there, and the water is essentially gaining or losing the heat because of what's happening with the reaction itself. So that you need to understand there's a huge difference here. All right. If you see anything in a problem about, there's a reaction taking place and it's being burned or it's combusted in the water or it's reacted, don't add the mass of the substance to the mass of the water for your Q equals MC delta T. Just use the mass of the water itself because you're not forming a new substance. All right. The water's just going to essentially be where the reaction is taking place. So we don't add the masses together. This is a huge idea, and you need to be very careful with the difference here. If you are dissolving a solid in water, you add the two masses together for your mass in your Q equals MC delta T. If it's just being burned, combusted, or reacted, you just use the mass of the water only. You use the mass of the substance later on in the problem, as you'll see. Now that we know the difference here between the dissolving and the reacting, we can do this problem. So since this example has the sodium carbonate being dissolved in the water, we have to add the masses together because essentially this solid is now being incorporated into the water to form your solution. So our total mass here is going to be the 75.0 grams plus the 5.19 grams of the solid. So we have 80.19 grams as the mass here that we need to use in our specific heat equation. And this is because it's dissolving. So now we're going to do Q equals MC delta T here. We're trying to find this molar enthalpy of dissolution, which essentially, anytime you see this molar enthalpy part, they're telling you they want kilojoules per mole. All right, don't be fooled by the wording here. There's a lot of weird wording involved with some of these problems. Molar enthalpy is talking about kilojoules per mole. So when we plug in here, Q is going to be equal to our mass, which is our total because it's dissolving. So it's 80.19 grams here, times the specific heat. We didn't get any information about specific heat. We're assuming this is going to be the specific heat of water. So we're going to use 4.184 joules per gram degrees Celsius. You do need to know that. Times delta T. Well, they just told us in this problem that the temperature increased by 3.80 degrees Celsius. So essentially that is our temperature change. We don't have to do any actual subtraction here. So we're just going to plug and chug, solve for Q. All right, so when we solve here for Q with sig figs, you should get used to sig figging here kind of as you go. That's something that AP does. So when I do this for Q, I got 1270 joules. Remember, this is the heat here. All right, joules is your unit because you solved for Q. And understand, this would be the heat involved of the solution. So this is the amount of heat that was gained by the solution. Well, that's not what we care about here. We care about the heat or the Q of the reaction. If the water gained that much heat, where did it come from? It came from the dissolving. All right, so we need to flip the sign. The negative 1270 joules is the heat that was lost by our reaction. Obviously, it wasn't a reaction, it was just a dissolving, but you understand here the difference. The Q, the positive Q, the 1270 joules was the amount of heat that was gained by the water, had to come from somewhere. It came from the dissolving. So when the dissolving took place, all right, we lost 1270 joules here. So when they say that we want the molar enthalpy of dissolution, we need to get this to kilojoules per mole. So we know that we lost 1270 joules, all right? And that was the heat involved with what amount here now of the solid. So this is where we would use the 5.19 grams, all right? So notice the difference. Because we were dissolving, we had to add this to the mass of our water for our total mass in Q equals mc delta T. But now that when we're ready to find the kilojoules per mole here, we're just using the mass of the solid itself. So right now I'd be in joules per gram. Well, I need to be in kilojoules per mole. All right. So we know there's 1,000 joules for every kilojoule. Joules will cancel. So right now you'd be in kilojoules per gram. So we just have to do a molar mass here. This is sodium carbonate. When you do your molar mass, it should be 105.99 grams for every 1 mole. So grams cancel, and now you would be in kilojoules per mole. Again, realize this was negative. So essentially, this is exothermic. All right, the water got warmer here because when this dissolved, energy was exiting. So when we watch our sig figs and do our math, it should come out to be negative 25.9 kilojoules per mole here. So this is just giving you an idea about how to do one of these problems when you're dissolving a solid in the water. All right, so definitely understand the process, how you use Q equals mc delta T, and then you do your sign change because we care about essentially the reaction that took place, not what was happening with the water itself. And anytime they're talking about molar enthalpy, just get to kilojoules per mole. Obviously, watch your sign in your answer as well. Now we can look at one more example here. Again, this is going to be a little different. There are a lot of variations of these calorimetry type problems. So this one says we have 1 liter of 2 molar barium nitrate being mixed with 1 liter 0.5 molar sodium sulfate, and they're mixed in a calorimeter. We get a white solid barium sulfate forming. The temperature of the mixture increases here to 28.1 degrees Celsius. We're assuming the specific heat is 4.184 joules per gram degrees Celsius and that the density of our final solution is 1 gram per milliliter. We want to calculate the enthalpy change per mole of the barium sulfate that forms. That's important here. We're going to be specifically looking at the enthalpy change involved per mole of the substance that formed. That changes the problem a little bit. But the first thing you should realize is here, I'm mixing two substances, I'm doing a reaction, I'm concerned or I'm worried about here for my answer, one of the substances that is forming. So probably need to write the reaction that's actually taking place here. So we have this barium nitrate, all right, reacting with sodium sulfate, and it's going to be a double replacement reaction. We already know one of the substances forming is going to be the barium sulfate according to the problem. And then when you actually, do your switch here, symbol charges crisscross, the other substance is going to be sodium nitrate. All right, don't forget to balance it. The only thing we need here is 2 of the sodium nitrate. So this is the equation that's taking place, but realize when we're doing the problem, they're specifically asking about the enthalpy change per mole of this substance. So that's going to be important later on. Before I can even worry about that substance, I have to find the actual energy change involved with the reaction. So before, I can even worry about the per mole of BaSO4, I need to know the energy change involved here. So you're going to need to use Q equals mc delta T, but realize you're going to need to get your mass first. We mixed 1 liter of the barium nitrate and 1 liter of your sodium sulfate here, and we're going to assume this density is 1 gram per milliliter. So remember, you use your density to get your mass. So just so you realize, your new total volume of solution is 2 liters, okay? And we're going to use here our liters for every 1,000 milliliters to get to milliliters. And now that we're in milliliters, we can use our density. They told us the density of this solution is 1 gram per milliliter. Obviously, this is a very simple conversion because it's 1 gram per milliliter. It doesn't always have to be one. I just wanted you to realize that you do need to get the mass of the solution here involving the density. All right, so you get the new mass of your solution to be 2,000 grams. Now we can plug into Q equals MC delta T. All right, we need to find the Q here of the reaction. So Q is going to be equal to the 2,000 grams for your mass. Watch your units. C is going to be the 4.184 joules per gram degrees Celsius times your delta T. The final temp was the 28.1 minus the 25 for your initial degrees Celsius. So final minus initial. When you solve for Q here, you do get 25,900 joules. All right. But realize that's the heat that is gained here by your solution. So where did this come from? Well, that was, or it's coming from the reaction itself. So the reaction lost that much energy. All right, you need to realize when you're measuring the temperature change here, you're measuring the temperature of the water itself, if you will. Well, if the water is gaining energy, it had to come from somewhere. It came from the reaction. All right, so you have to do your plus Q minus Q here, essentially flip the sign. So now we know that this is the amount of heat that was lost by the reaction itself. But we care about the enthalpy change per mole of the BaSO4 that's formed. So we're going to have to do a limiting problem here because we need to know how many moles of BaSO4 actually formed in the problem. So if you look at your original amounts here, we know that we had 1 liter of 2 molar barium nitrate. So obviously, if you figured out the number of moles of that, all right, if you got rid of your liters, you're just starting with 2 moles here of this barium nitrate. So when you use your equation, all right, we know according to the balanced equation, there's 1 mole of your barium nitrate for every 1 mole of the barium sulfate, which is what I care about. So when you plug and chug this, obviously you would get 2 moles of the barium sulfate forming, right? If the barium nitrate is your limiting, right? Because we need to figure out how many moles of barium sulfate are going to form if we're going to do the enthalpy change per mole that formed. But then we need to look at the other reactant here. Again, they told us we had 1 liter of 0.5 molar. So if you get rid of the liters, essentially you're starting with 0.5 moles of the sodium sulfate. So when we use our balanced equation here, there's 1 mole, all right, for every 1 mole of the barium sulfate again. So when we plug and chug this, we get 0.5 moles of the barium sulfate forming. So obviously the lower of the two, all right, this is going to be your limiting, right? The sodium sulfate limits. So the amount of barium sulfate that actually forms is 0.5 moles. So this is the enthalpy change, which we already found here. We know that this is the energy that's given off by the reaction itself. And now we know how many moles of the substance we care about here that are forming. So the reaction itself lost 25,900 joules of energy, and that's for every 0.5 moles of the barium sulfate that formed. So be careful here. They were asking us specifically about the product. We need to know how many moles of that product actually form by doing our limiting problem. So it's all in the wording here. So this would just give us the joules per mole of the barium sulfate form, but now we need to get this to kilojoules per mole. So that's easy. We know there's 1,000 joules for every kilojoule. Your joules cancel, and you would be in kilojoules per mole. So when you plug and chug in sig fig, negative 52 kilojoules per mole here. All right, so this was just another version of one of these problems. And again, it's all in the wording. These problems, you have to be very careful with the wording to see what you're looking for, but we needed to get the mass of our solution, plug that into Q equals MC delta T to find the energy gained by the water, realizing that we cared about the energy that was actually lost by the reaction itself. Once you have the energy lost by the reaction, you put that over the total moles of the barium sulfate that formed, and then you just get it to kilojoules per mole. So be very careful with these problems. pay attention to what you're solving for, and make sure you're reading everything carefully here.